This is 15.27. In this problem, it's a pulley problem where we have a force being applied in the y direction right here. And I drew a little miniature person to represent that. But we got to follow the chord, see what's happening. And we really should do a free body diagram about A. And so if I do a free body diagram on A, I see we have two tensions pointing up, and then just the mass times gravity pointed down. But what we need to realize is that each one of these tensions is the force applied, and they gave it to us as a function of time, 100 plus 5t squared newtons. Okay, they want the speed when t is equal to 3 seconds if starting from rest. And we have the mass as 20 kilograms. Alright, so let's use impulse momentum theory, but we should go ahead and see if, well, they told us it's going from rest, but if you wanted to, like I did in the previous problem, you could check F at t is equal to 0 and compare it versus the weight. So it ends up being about 200 newtons versus the weight ends up about 196.2 newtons. So it technically should be accelerating, but they told us in the problem it's starting from rest. So we know it will move at least the instant we start the problem. We don't have to wait till some time t before motion begins because the force will be greater than the weight. And by the way, there's a 2 here because I've got two tensions if you're trying to calculate that in your head or something. I put a 2 right there, and I'm about to do that again. So let's conserve, or I'm sorry, let's use linear impulse momentum theory. So L1 plus the summation of our impulses, and there is a summation this time, of all the forces acting over a time period T1 to T2 gives us our new linear momentum. We're just going to talk about the mass moving, so it would be m times the velocity of the mass plus, now I'm going to leave a blank right here. I'm going to go ahead and put in the force impulse, or the impulse we're going to get from the force, and that's the 100 plus 5t squared newtons dt from 0 to 3 seconds. We also need to consider, this is only one of the impulses being applied. The other impulse is applied by a constant force, and that's our weight. And it's going to be acting in the negative direction. So we'll have a negative mg, and it's acting for 3 seconds. So we don't have to integrate that one. And this is going to give us some new, call it velocity at 2. Okay, so what did I put this here for? Well, from the free body diagram, it shows that we have two tensions going up, so we could either integrate each one separately and add them, or just throw a 2 right there. Okay, I get this being 0, the initial momentum, because it started from rest, and then carrying through the integration, I get 100t plus 5/3 t to the third, and that needs to be evaluated from t is equal to 3 to 0. The constant weight term or impulse term gives us 588.6, and then we have a 20 kilogram times our velocity at 2, and we can solve that for the velocity at 2. It comes out about 5.07 meters per second.